Hello, and welcome to another video. Um, so I thought I would pick up where I was. We were implementing so we're working on the Git, build your own Git in the Codecrafters, and we're currently trying to read a blob object. So what is happening is, well, we're trying to print the thing, and where I wanted was this thing. So currently we've done a bit of stuff to like kind of do error checking and whatnot. So I think I want to copy some stuff down into there. And I actually realized if you don't pass an extra argument after the -p, it will seg file, or if you do the same there. And I think the reason is that. So what are we doing now? So I guess this will do some things. It's not telling me any help, and it will return 1 just to say that it has failed. But if we try and so we've got nothing in this Git directory. What we could do is try and create a Git file, and I'd rather not kind of mess up that directory and do it in the one I'm working in, just because it's got a bit more stuff, and I have already made it. And then this temp/git can be completely made by my tool, which will be kind of cool. So if we get to here, I've actually created a file and if we go git cat file, what do we want to do? So maybe I'll step through how like Git would find the process. So I've currently got a Git commit that is just adding a single file, and it's got it was just a little test just to do things. So what does this commit do? So first off, we would that one, thanks. We would get the commit ID, and we already know that there's a bunch of stuff under Git objects, and so there should be a 9.6 and a B6, and this should have some stuff, and it should have binary data, and we'll get to that. But if we use just normal Git, so this is the normal Git that I've installed with my operating system. If we now run git cat file -p of that commit ID, what it will do is it will kind of say, well, the parent of this commit is this 2e thing, the author is this, the committer is this, and the commit message is what follows. But what's kind of interesting is it's got this tree. Get out of it. It's got this tree, which I'm going to kind of yank into my clipboard. And now if we kind of look at what that tree object is, it will give like a bunch of blobs. So it will that one's got a tree, which is kind of interesting. That's a directory. So this directory will have another kind of tree like this. So this is kind of a point in time. Yes, that go there. It's a point in time snapshot of what the commit is, and so in this there's a blob thing, and there is also a Git object thing for this, and what was it? 787898. So it should have a thing, and it has garbage. It has slightly less garbage in because the file is small. And if we cat file minus p of that, if we get cat minus p of that, it will tell us A. So that's the contents of the file. So that's like roughly how Git does it in the back end. I think they have a link to like the internal docs and stuff, and I think there was one for like plumbing. So like the Git docs, if you kind of read through it, where does it tell you the title of the book? It's just a book. I think if we full screen, is that the title of the book? I don't know. Maybe this book. Yeah. So this kind of tells us a lot of things. There was also just a reference manual, which that also tells you a bunch of things. The Git docs are actually remarkably good, I would say. But yeah, it kind of tells you a lot of things. But anyway, where did I get to? So the problem is that this file is this file is it's got like some binary data in it, and the problem is it is compressed using zlib. Now, luckily, zlib actually has an RFC. What are we? RFC 1950. And it was done in 1996. But yeah, this is the format specification for version 3.3. And what I might do is I've created a a.temp file, which kind of does this. So this is the blob ID that we were looking at before. And the output of that gave us this hex, and I've also kind of made a binary version of it. And so these are all the bytes that come in. So the thing is, zlib is a stream-orientated thing. So it really cares about just bit by bit what is happening. And it's kind of funny because if you're reading bit by bit, as they are, you would think that this is bit 0, like this column. But actually, that is bit 7, and it will tell us there. Basically, that's the order of bits that you will take, which I kind of get, and it doesn't really change how we're going to do things. But how we kind of generate things are interesting. Like, for example, so it's basically saying the stream has this structure. It's got a CMF and a flag, which are 2 bytes. So these are that byte and that byte. And the CMF is, potentially there's more stuff, like the flag dot, dict ID, which 4 more bytes. Otherwise, it just has all the compressed data, and at the end, it's got a checksum, which I guess we'll have to do that as well. So here we have the CM, the compression method, and it's bits 0 to 3. So that is these bits here. It's kind of interesting because like the 0 is the rightmost, and you kind of take all of those just as one number. So we get this number here. And if you convert that back to binary, decimal, we get 8. And we'll see here that if CM equals 8, it denotes the deflate compression. So it's kind of interesting. Everything has to be CM8. So this is almost like a magic number, like zlib compressed stream will probably always start with 7.8. This 7.8, sorry. I was getting confused before doing some prep because they both start with 7.8, but I want this one because it's got the 001, single 01. So we get that compression method is that. The C info we can take, and this is again just taking from here all the way up to here, but as kind of one number. And we can do this. This is possible with like a bit twiddling and stuff and shifting and masking, all that sort of cool stuff. So what happens then is we get the flags. So the flag byte has fcheck, which is the bottom 5 bytes from there to there. So that's there. We don't really care what the value is. But then fdict is the next one, and flevel the leftmost two, these two things here, which just happen to be 0, but I'll put them out because this is what is happening. So fcheck is like just a checksum. So if we get CMF times 256 and add on flag, we should get something that is a multiple of 31. So 120, we could not do that. We could sometimes does weird things. We could jump into Python and we could say what is 120 times 256 plus 1. It is a big number. Not too big, I've seen bigger. But what happens if we mod it by 31? So this will give us the remainder of a division by 31. In essence, it can tell us whether it is a multiple of 31, because if it's a multiple of 31, the remainder will be 0. So this means that we know that these two are a valid zlib header, and we can see fdict is not set, so we don't have an extra dictionary that's coming after. In flevel, we don't really need. It's only there to indicate if recompression might be done. So at this point here, all the compressed data comes. So the compressed data comes using the deflate compression algorithm, and that's another RFC. So we can see this RFC here, the deflate compression, and this is actually by the same guy in the same year, and you might note that it's just 1 digit up, so he probably just emailed both the RFCs in. So this has a bunch of stuff. So it has similar notation, and the 7th bit is on the left as before. The problem is that, I don't know, but how you pack that into bytes, like when you're constructing bytes from this bit stream, that starts with, like, so we'll be going there, and then up to there, and then across. And this will be kind of how we operate. We could kind of make this a thing by just doing rev on it, and then we would just go line by line like normal, but I'll keep it original bytes just as it is. Because that's what the compression is. So how does the deflate kind of start? It describes this, and sometimes if you're doing data elements, then you want to start with the least significant bit, and if you're doing a Huffman code, then you're doing a rightmost significant, rightmost bit. Leftmost bit, sorry. The most significant bit. So, like, yeah, this is just like a weird thing, but it's only really relevant if we are constructing Huffman codes, which we potentially are not. It depends on what is happening in the header of the deflate stream. So what the thing is like this is giving like a whole lot of thing that you don't really need. Like at the moment, it's kind of describing Huffman coding, and this will further kind of describe it. There's some limitations and whatnot. So then we get to right. So details of the block format. So we can say here that the first bit, which is this one here, is the BF inval, and then the next two bits, which, because they're not a Huffman coding, we take it like least significant bit is the first one. So we would get something like 01. So it's kind of treated the same. So what is this? This is a so the first bit is set only if it's the last block. So basically it's saying this whole thing is a single block. Maybe if we like this. So this whole thing is a single block. And it is fixed Huffman. And so now what are these bytes doing? These are just the same things. So now we like have used these, I guess, so we can kind of mark them as used, and we can see what comes next. So what I get is we have a certain type, and if we kind of scroll through, we can see what it is. So 01, this is our compression with fixed Huffman codes. So the fixed Huffman codes means that we have a kind of set table of things, which makes it a lot easier. So yeah, I guess what you need to do is kind of step through like each of these, like see if we need to like read 8 bits and kind of construct a data, I believe. Talking making me croakier today than usual. Right. So from what I gather, we just need to kind of read 8 bits and see what happens if we do that. So I guess what is the first value? So this is going to be 0101, but that's only 5, so we would also get a 10, no, not a 10, an 010. So this is 8 bits. Where do we see this in? Do something like that. So yeah, that's 8 bits. So at this point here, we would try and see whether it fits in with one of these ranges. And eyeballing, like surely this would go up to 01 at some point. And this one is quite low, so this would kind of never really meet. But maybe we should actually only read 7 bits to start with. So yeah, maybe we would read these 7 bits and we would see that it doesn't fit in this range because it's got a 1 at the start. So we would read another bit and then check within this range. So we could check whether it has 1, 1. That would make it invalid, or if it's 0, 0, if it starts with that, then it should be in a different one. But we can see that it doesn't. So this is likely in this value here. So then we just get this number as is, I believe. So we could maybe we could make this just run Python for a little bit. So what is 010011? What is this? It's 73. So we could say this is 73. And what happens before? So the code lengths are then kind of used with like not this one. Oh, like maybe it is. Yeah. Right, so I think we have to like decompress it from like a kind of like a run length encoding first, and I think that was kind of mentioned in this. Yeah, so you do this like duplicate thing, which is kind of based on a LZ thing, but it is noted that yeah, so it's related to this compression format LZ77, but we should not really look at that because that is patented. That potentially not anymore. Software patents shouldn't exist. But yeah, we can kind of follow this kind of sequence here. I do sometimes find reading RFCs a little confusing. But yeah, so we get this 73, and what has happened with these? Is this the so it's not that. So I think this just means it's a literal, because they do like this weird thing. So you can either have 0 to 255 or 3 to 258, and they kind of merge those two together into something that doesn't fit them all. But these ones kind of represent things that you might add another digit on, which is interesting. So what did we have? We just had 73. So this is just the literal value 73. Which is that right? So we can say it's an odd 73. No, it's not odd. But we could probably do a help on odd, and yeah, but what's the thing that does the opposite of odd? Because that's the ordinal. We want. Is it just true? It's just true. So that's like an I. I don't know if this is right. I'm just not sure that is right. Because there's also potential that when we are reading this B type, it's actually one no, which is a dynamic Huffman code, which would mean that we would be like getting a bunch of extra bits to define the code. it might be doing that because like I never occurs in the thing. We would want something like what? It's like we just had A, so we would want something like 97 to pop its head in the door. I wonder if so 0B 101010. That's like a bigger number. So that's reversing it. So maybe I'll do something like that. So we kind of generate the values. So we pick as we pick the bit, we will shift it on. So maybe this would end up like 101010, and that is a different number. So that's 146. But that's also kind of fitting in the. Ah, no, 146 is in a different realm. No, because we would get just the 7 bits first. And so that would be 73. So this is trying to fit in this range here, but it doesn't start with 00. So we would add on that extra bit and try with this range. And so it would still kind of fit in this range. Though should it not? Because 10, a whole bunch of ones. That is still less than that. Or maybe. We want this to be that minus the start, which is what is it? 0B 1100 48. And what is that? What was it? 73 minus 48. Brain's not working. 25, and 25 would be a like, yeah, just weird character. Something like that, and that would be a literal value. That would still be in there. But what if we are doing it the other way around? This would be 146 would still fit in there, and we would do the minus 48, and this would bring that I don't need that. That's just going to be a 98. And what was 98? 98 is a B, which I also wouldn't expect. I would expect it to have an A somewhere in it. So I think I'm not on the right track with this. So I guess that means that like we have the Huffman coding, the dynamic one. Yeah, so we have to do this first. So, dynamic Huffman codes, easy. 3.2.2. 3.2.2. Ugh. It's been a few years since I've been doing Huffman coding. Yeah, I haven't even done zlib decompression, but I mean, really, all it needs to do is kind of read the bits. What's this trying to tell me to do? Yeah, so I guess we need to read something. Not that one, this one. Oh, right, so the code links. Crazy. It's compression all the way down. Hmm. So what do we have to get? We How many bits do we need to get? Because these are empty bits. How much would HP get? It's like a weird number of bits because you might have 19 or a whole lot of other things. That's not what I wanted. Is originally in, oh no, that's just his name, I think. Um, right, all right. So what if we get and we'll try another time, another way. So we get 5 bits. So we would get 1 0 1 0 in that order. I don't know. Who knows? And oh, like maybe we need to try 4 bits first. And this is thing -4. And what is that? That would be like um 1 0 1 and 9. Yeah, I thought it might have been 8. So that is 9. And I don't get code length 0. It's not code. Hmm. Oh, right. I think I've got this. All right. So H lit is going to be uh, this. Oh, this. I don't know. Who knows? And H dist is going to be like 5 bytes. So this is going to be these 5 bytes, I guess. Except reverse, but can we just reverse that line? Um, um, so that's going to be those 5, and then we get another 4. So that's going to be 111 O H C L is 1110. So we get all of that, and that's all the way from there. Right, so then we get HC len. So that's like nearly 16. This is 10. And this is like 16, 18. Or and this is potentially or like 10. It's palindrome. When this is 7. Who knows which order I'm meant to be reading stuff in. Um, and packing stuff in trial and error doesn't hurt. Right, so here we get HC len. That's this last one. So this is 15 plus 4. So 19, and then times 3. 19 times 3, I should know. 57. And then we have like code lengths. So then we should have a bunch of 3-bit integers. I gotcha. So we'll get 19 of them. Oh, right. So 16 equals 100. 17 equals 100. 18 equals 111. 19 equals 011. 20 equals, where did I get up to? 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. So we did that, and then 010. 010. And these change at 18. That makes it 0, and then this is 8. I think 7 equals So that means 010 then. So it's 000 and then 110. Uh, 000, code, 110. That needs to be that code equals, so that was 000 and then 110, then 000 again. 000. Right, and what is this x meant to be? 9, then 6. Hmm. I don't get it because this is going to be what 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. It just happens to be 19, but like, what if that wasn't 15? Um, and yeah, code length of 0 means something isn't used, and we do have a couple of zeros, which would always be zeros because they are 3-bit integers. I don't get this that we have that because, like, what if it is um, not 19? I guess we just happen to have 19. Weird. Anyway, I think I want to do this. Something like that. We only got pod there, and that was wrong. Right, so where did we get up to with this? So we should be like 100, 100, 111, 110, then 010. Yeah, so this should be 010, 010, and another 010. I think I off read by 1. Ah, not that one. This one that go up to here. And then we get 001 would get us to there. 001. And then we should get the 000. And then 011. And then 011. Then it will be 100. Then it will be 000 again. It will be 011. then it would, I would do this. So from here we did 011, so we would get 100, which would get to there, then you did 0, then 011. So we should just be on this byte here. Not that one. And this is 000, and this is 001. This is also 001. This is also 01. This is 111. No, we should have an 010. I'll make that a 110, and that will make this 101, and this will be 000, and we would end up there, I think. Now, is that right? How many things do we have in here? So we have we have not that, thanks. We have 8 times what we got, 6 there, 1, 2, 3, 4, 5, 6, and that's what the thing says. And then we have 7 from that first byte, and then 4 from that bottom byte, and we should have 59. And I believe that is what I. No, it should be 57. So means I did a mishap somewhere. 100, 111, which would put us to there, and then 11, and then 010, 010, and then 010, and then we would get a 1, which would take up that, and then we would get 0, and then 11. So 11, which would, yeah, so I think I've done a thing here. This 100 should be 0, and this should be 1. And that would be 1. Pretty much we're shifting everything. And then this will be 010. And then like that. And then 101. And that was an O. So 101. So it will be 0, 0, 0. Another set of zeros. And another set of zeros, and end up with there. Right, so what does that give me? That gives me 6 lines. Was that right? 1, 2, 3, 4, 5, 6, 7. No, 6 down from there. So this would be 7. We still have 7 bits in the first one. And what do we have down here? Just 2 bits. So that should be 65. It's like a different amount again. Should have 57, which makes sense. We're reading 19. Yeah, so we are reading 19 things. which should be the 15 plus 4. So there should be 57 bits. Hey. Right. One, two, three, one, two, three. Then 1, 2, 3. Then 1, 2, 3. Then 1, 2, 3. And then 0, 1, 0 again. Then 0, 1, 0 again. I think I screwed it up there. So we should have 3 010s in a row. Let's just make it like up there, just in case. I'll do that again. So 010, this should be 010. And then we should have a 1. 010. That would give us the 1. And then we would have a 0. And then like 11. Gosh, this must be fascinating to watch. Fascinating. And then we should have 100. So that'll put us there. And then we'll have a 0 again. And then an 11. And then we'd be down here to get a 0, then a 1. So we'll be there, and then we'll be looking at another 1. So it'd be there, and then we'd get an 010, 010, and then we'd get a 110. So 010, 110, and then 101. And then we have significantly gone there, except it was 0 before. No, it was 0 before. So we can change this back to a 0. And this kind of looks more right. So how many did we have of those? We had 6. So this should be 6. We still had 7 at the first one, and we got 7. Well, we got 8 in the last one, so that should be 63. And I think it's not right. That's what happens when you go through manually, I guess. I guess we would 57. So we got that 7 from the first one. So where would 50 divided by 8 get us? It would be get 6.25, 6 and a quarter of bytes more. So 1, 2, 3, 4, 5, 6. And then we would go a quarter. So like, yeah, here. So this is where we are meant to be. Make like a little note. And maybe I want to go this way, because then we can kind of be a bit easier. So 100, 100, easy. 111, also easy. 11, easy. And then 3 010s, 010, 010, and 010, easy. Then a 1, which would be there, and then 0, and then 11, and then 100, then zeros, then 11, and then 0, and then and then 1. So we should have 2 1s. Then 010, 11. Yeah, this looks like I've done the thing. Yeah, so the 11 went there, so this would have. We can check, but I think this would be a 1. Maybe so we can check if that was. What will I do? Now redo that, but take me back to. So this should have the same up in there. Yeah. So we should have 010, a bunch of 1s, 010, then ending with that, then that, then that, then that one, then 111. Yeah, so that is what it was. So if we do that, and then the next one down was the 10. Cool. And this looks like it is more correct. So if we did this equation again, so how many lines did we have there? We had 6 lines still, and we had 7, and we have used 2 bytes of the next one, and that should be 57. So 57 bytes was how many we thought there would be. So what happens now after we get the code length? We then get 8 lit plus 257. So 8 lit plus 257. 8 lit was 18. Yeah, we're going with the maybe do that one. And not that. I'm going to go with the it's that one just because the code link kind of made more sense. So what is 18 plus 257? That would be 275. So 275, just confirm that. So 18 plus 257, 275. Perfect. It's good practice to do like mental arithmetic. You don't do it as much as, well, I find I don't do it as much as I used to. But it can be a bit quicker, save you going to a calculator. But sometimes it is good to check. Right, so we have a bunch of codes, and now we have code links for the actual alphabet. So code links for literal link alpha. So this should be 275 bits, not bytes, bits, and that came from a lit plus 257. Gosh, that's a dyslexic thing. Cool. So code links for these, but they're encoded with the Huffman table is above. Cool. So I guess we need to read a bit. It would be more useful if this was kind of printed out a bit better. So Huffman table for code links. So this is 0, 0, 0, 0 to if 1, 1, 1, 1. So that would be 0 to 15. And what was that? That was 0 to 15 at liberal. And so then we'd have 16, which would be 1, and this is previous 3 to 6 times next 2 bit. It's indicate length 0 equals 3 to 3 equals 6. Easy, that's fine. So 17 would be if we had a 1 there, that's easy to find. And so this is repeat code length of 0 for 3 to 10 times 3 bits. Next 3 bits indicate length. So I guess 0 equals 3 to what you could get up to 7 equals 10, and that makes sense, that range. And so then we'd have 18, which would be 1, and we'd have a 1 there, yeah, like that. And this would be repeat there, code length of 0 for 11 to 138 times 7 bit of 11. Easy. I think that is doable. So maybe I want to have a second table just so I can see these. And so these are the ones we just read. Are these ones? No, that's fixed. Oh gosh, man. Code lengths for the code alphabet given just above. Right, so we've just given the length of what we should read for the next number of code lengths, and this should be encoded using this thing. Right, I think I've got this. So what we can do is down here we have some stuff to go. So I guess we can say we've swallowed this. We have data elsewhere. Kind of what it is. So here we can say, what are we up to? So here we're reading we're basically trying to see whether it fits in with the this thing here. So we would get 4 bits because that is the lowest number of things, and so this would be 4 zeros. It just happens to be 4 zeros from down here. So we can say that this is just 0. uh, literal 0. And I guess this kind of makes sense. Like we've only got one character that we need to output. So I guess we would have 0 for everything that isn't an A. And there's an A hiding in the starter here. Like I can smell it. I wonder also whether this so this is what 6 bytes, but we have actually used up 6. So it's really 5 bytes plus 6. 5 bytes plus, well, no, we can say 6 bytes minus 2. We have used 2 of them. And that's like kind of, we've only got 46 bits of data left, which makes it interesting that this is kind of saying that we have this many things. I wonder if this means that what we construct adds up to this, like the Huffman table that we construct out of it, which also makes me wonder whether I'm meant to be pulling stuff from the other side, but who knows? Right, so and like how did this kind of end up into it? Because things that only go up to what, 18, we can get 18. Like where is that mentioned that we have? I kind of want to look at some code, but I need to find something that is copyright appropriate. I think zlib is actually copyright appropriate, that I can take it and do what I want with it. But I think it also mentions that you're meant to, like, say, you're not allowed to say that you stole it. Whereas I want to kind of read the code to understand it, and then I'll write my own code based off the RFC. That kind of makes sense, because this kind of bit where you're decoding stuff can be quite tricky. But yeah, it is what it is. And I know it's probably not the most exciting to watch, but hey, maybe it is. Right, so yeah, we've got this many things. So I guess this means that we're now just decoding stuff. And we have a 0. The next thing, if we continue down this track, would be 0, 0. We have like a bunch of zeros. So we would have one up to there, and then one up to there, and then this one will be different. So 2 more zeros. They're just zeros. The next one, we would get something like, what if we, we kind of do need that. I kind of want some more space. Maybe something like that. So this is going to be 1000, and so this will still fall in this range. Cool. So this is a literal 8. It's just what it is. So that's going to be the code length of the fourth thing. Fourth thing code length 0. 8. because we had 3 literal zeros. So that's kind of my understanding of it. And so that would get us to there. We could do something like that. And then we, 11. And we would take all of these things, take all of the bytes, I believe. We go back now. Literal 3. 15. So where did that get us? Was that just there? Yeah, so we had 0, 1, 0, and then we have another 0. And then we have 1, 0, 1. There. 1, 0, 1, which is a literal 9, and this will be the 7th. So this is, I don't know if this is the right thing meant to do. So this is that. Then we'll get the 101 again. So this will be just take me there and then find that, and it will be that. So that would have read that, and then we have some zeros, and then 100. And then also this is a literal 246, and this is the 10th thing. And like, how many things are we meant to be reading? Like, I feel like I don't know. It seems like I'm not going to make up the like massive 275 bits out of this. Like, it's just not going to happen. Yeah, I just. So this is a literal 7, and it's the 11th thing. And then I just kind of run out of data like that. Well, I've got 2 more bytes, but what can you do with 2 bytes? So I guess I kind of wonder, we can see what this thing is. What is this? It's zlib compressed data. It doesn't really tell us much, but can we get some stuff out of it? So maybe we can copy this to. I kind of want to see if we maybe also open a.10, because I want to see where the deflate started. So it was just after 2 bytes. So 1, 2. Why is it read only? I've vimmed it. So now what happens if we do this? It's just data. So it doesn't really know that it's deflate data. I don't know. I think I might need to kind of sit on this and mull it over, if that kind of makes sense. Because this is, I mean, doing it by hand, like, is very slow and mundane, but I am wondering whether I am doing the right thing. Like, is it a fixed Huffman or is it not? If it is, then why am I getting like the requirement to read a lot more? Which kind of makes me think that it is actually a fixed Huffman, in which case, so fixed Huffman, the value would like 7 bytes. 010. Yeah, so I guess this is actually read 4, 5, 6, 7. So that doesn't fit in this range. So we read an extra 1, and then we had 8 bytes, and it fits in this range. And if we reverse it, it still fits in this range. Maybe I need to like rethink Huffman coding again. Because, yeah, I don't know. I don't know. You can do like a bunch of other things. Canonical Huffman code. Yeah, so we're doing decompression. What does it say? So, like, we haven't constructed the Huffman tree. I think surely that's what it's called. But we haven't constructed the Huffman tree. We've just kind of gone for the literal values. But like, if you did the Huffman tree, then it would probably work. But yeah, maybe I don't know. I think I'm going to leave this here and have a think. And I think this is potentially worth just going through my thoughts on like zlib compression. Gosh, that could be like quite clickbait. People will be like, "Whoa, he thinks it's really bad," but really, it's just my thinking process going through it a little bit. Yeah, I think for now, thanks for watching, and I'll see you next time. And hey, if you've got any comments, like let me know. Maybe you can point me in the right direction. Otherwise, I'll just read more RFCs and stuff and try and work it out. Remember what I did in uni a long time ago. But yeah, thanks for watching. See ya.